When most people picture a cryptocurrency wallet, they imagine a secure digital vault, a closed environment where their Bitcoin or Ethereum sits behind a lock. In reality, there are no coins inside your phone or on your hard drive. Every digital asset you own exists entirely on a decentralized network ledger, logged as a global state entry. This diagram illustrates the actual boundary. A cryptocurrency wallet does not store value. It is strictly a local key management system. Its only job is to generate and store the cryptographic signatures required to authorize changes to that external network state. To truly grasp how custody works, we have to map the mathematical pipeline that translates a string of random entropy into a programmable on-chain constraint. Tracing this exact path explains why the entire industry is currently abandoning traditional private keys in favor of institutional multi-party computation and account abstraction. The entire architecture of ownership begins with raw cryptographic entropy, a completely random sequence of numbers generated by your device. Because raw binary is hostile to human memory, the BIP39 standard maps this entropy against a specific list of 2,048 words. This creates the seed phrase, a human-readable backup that can deterministically reconstruct your root cryptographic key. From this single root seed, wallets deploy a hierarchical deterministic architecture based on the BIP32 standard. By running the seed through a SHA-256 function, the wallet creates a masternode, mathematically deriving an infinite tree of distinct child private keys. At this stage in the pipeline, these child keys are completely agnostic to the network they will operate on. They are just raw mathematical potential. This HD structure is why a single 12-word phrase can simultaneously control assets across entirely different Layer 1 and Layer 2 virtual machines. You only need one root to regenerate the entire tree, but a private key alone cannot receive funds. It must be translated into an on-chain address. As we see here, an address is an identifier that contains encoded conditions, specifically a required signature and script logic, that must be met to spend the asset. Bitcoin and Ethereum derive a public key from the private key, then aggressively hash it down using RIPE MD160 or KCAC256. This secondary hashing hides the full public key for quantum security and adds checksums to prevent user typos. However, this hashing creates overhead. Newer high-throughput networks require faster execution, leading to the pure public key model. Looking at the Solana network architecture, the secondary hashing step is entirely removed. The address is simply the raw 32-byte ED25519 public key. The syntax of a cryptocurrency address reveals the exact cryptographic trade-offs its parent network makes between security overhead and virtual machine execution speed. Architectural shifts have transformed the address into an active execution environment, where programmatic logic, rather than a static signature, dictates the movement of assets. This chart tracks Bitcoin's address evolution. Notice the shift from simple legacy formats at the top, down to pay-to-script hash and taproot architectures. A pay-to-script hash address requires the spender to provide a hidden piece of code, a script, and the inputs that make that specific script evaluate to true. Ethereum takes this further with contract accounts, deployed via opcodes. The critical architectural difference is stated right here: no private key. A contract account cannot initiate its own transactions. It is controlled entirely by its internal bytecode logic. The trajectory of address design shows a clear shift. We are moving away from simply proving your identity with a cryptographic signature toward proving that you can satisfy the programmatic demands of a smart contract. This shift toward programmable constraints solves the fatal flaw of the traditional HD wallet. The master seed is a brittle single point of failure. If the seed is compromised, the entire deterministic tree falls. Institutions use multi-party computation, or MPC. As detailed here, the private key is mathematically divided into separate shares across different devices. During a transaction, they communicate to calculate a signature together without ever forming a complete key. On-chain, the solution is the smart contract wallet, also known as account abstraction. Because the account is driven by code rather than a static key, users can program logic directly into their custody model. This enables social recovery. If an access key is lost, designated guardian accounts, whether they are trusted friends or legal services, can vote to authorize a new key, completely eliminating the risk of a lost seed phrase. These distinct approaches have created two competing standards for enterprise custody. MPC providers like Fireblocks utilize off-chain cryptographic distribution, while protocols like Safe and Argent rely on on-chain programmable accounts. Whether utilizing off-chain mathematics or on-chain logic, the engineering consensus is clear. The most secure way to handle a private key is to remove it from the user's hands entirely. The life cycle of custody is a strict mathematical pipeline. 12 words of raw entropy derive a deterministic tree of keys, which are then hashed into network-specific constraints, and finally managed by programmable thresholds. A crypto address operates nothing like a traditional bank account number. It is a strict cryptographic constraint designed to verify mathematical truths on a decentralized ledger. As the infrastructure scales, the intense complexity of key derivation, hashing algorithms, and script execution is actively being pushed out of view. The goal of modern blockchain engineering is to make this entire cryptographic pipeline completely invisible. Success for this technology means achieving absolute mathematical rigor underneath, while delivering the seamless, thoughtless experience of the modern web on the surface.